Hi, I'm Brian Litz, long-range shooter and ballistician. I'm here to talk to you today with a tip about truing or calibrating your ballistic solution. So in the perfect world, you would predict a trajectory, apply the solution to your scope, dial, and hit your target at long range. Now, in the real world, that doesn't happen exactly that way every time. The reason it doesn't happen that way is because of the uncertainties involved in using your ballistic solver. Most importantly, one of the common uncertainties is muzzle velocity. Okay, if you don't know your exact muzzle velocity, your trajectory predictions will be off at long range. And that's the most common thing that gets calibrated in a ballistic solver. So the way it works is you'll get a ballistic solution that's based on an approximate muzzle velocity, and you'll shoot at a target at long range to see where you're hitting. All right, and let's say your initial solution calls for 8.4 mils, for example. Well, you find out that at that particular range, you've got to hold 8.8 mils to hit the target. Well, in a properly written ballistic solver like the Applied Ballistics Kestrel, you can simply go and tell the ballistics solver that you actually hit at 8.8 mils at that range. The solver then reverse engineers what the actual muzzle velocity is to be consistent with that real-world observation, and it'll now apply that accurate muzzle velocity to your ballistic solution, and you'll be on at all ranges. Now, that's basic ballistic truing, and for most long-range shooting, that's the only truing that you'll have to do. Now, if you get into extended range shooting, like into the transonic zone, where transonic stability is challenged and you have some uncertainty in drag modeling, there's further refinements that you can do to your ballistic solution beyond that range that you calibrated the muzzle velocity. Again, in the Applied Ballistics Kestrel, this is accomplished through the DSF, or drag scale factor truing. And the way that works is the same basic way. You fire shots with your initial prediction, you observe the actual drop, feed that back into the solver, and then the solver then applies a correction based on your observed drop through transonic, and now your ballistic solver is calibrated at a more distant point and will be more accurate over a greater range. The important thing to understand about ballistic calibration is that it is a calibration exercise, okay? Any errors that you make in ranging the target or accounting for effects of direction of fire for Coriolis, for example, those errors will be calculated into that muzzle velocity that the computer thinks you need to hit that target. So whenever you're doing truing or ballistic calibration, you have to take greater care than you normally would to know the exact range, okay? You can't mill the target to get range. You have to have a laser rangefinder distance within a yard. You don't need to retrue your ballistic solution when you go to a different environment. The Applied Ballistics Solver accounts for the difference in environment and will allow you to make first shot hits now in a different environment from what you calibrated in. For more information, you can read the Applied Ballistics books, which go into more detail in layman's terms in a way that helps you understand this material better so that you can apply it in the field towards centering your group on the target.